All right. So we talked about CO2 and a bunch of other pollutants last lecture. Phew. And then we will talk about a little bit before we dive into today's lecture about how we can read the plot, and then we can actually interpolate or extrapolate the data set from the plot. For example, CO2 right here. So again, you got to take a look at the x-axis and then y-axis. And then x-axis is the year, and then y-axis is CO2 concentration. That was observed on top of the Mauna Loa. And as you can see, the CO2 concentration has been increased past about 50 years. Yep, 50 years. So maybe you can make a simple prediction. Use this plot, right? So this is CO2 concentration. This is year, and then CO2. And then we have observation data from 2010, all the way down to the 1960, right? And 2010, right here. Then 1960 is about 310 ppm. And then 2010, it's about 380. Although there's an annual cycle, but if you take a look at the kind of grand schematics, the concentration seems like increasing linearly. So if you assume that, I told you that we love to assume atmosphere as a one box, and then there's a source, and there's sink. If we assume the source, in this case, that source that driving CO2 increase past 50 years has been a human-made pollution, fossil fuel use. If we assume it is as the same kind of increase of the CO2 use next, maybe 50 years, 2060, let's assume that's right here. Obviously, you need to kind of measure that this thing, this is linear scale. So this is about 50 years. So let's say 50 years is about the same length of this thing would be right here, right? So let's extend this x-axis a little bit, like this much. And then 2060 is going to be right here. Then what we call it extrapolate is that basically you got to extend this line all the way out here. Then you can just extend your trend line all the way out here. Then you can kind of predict what's going to be a CO2 concentration in 2060, right? Like this. So we call it this as extrapolate. And then interpolate is kind of the other way around. That if you take a look at this plot, so this is the average aerosol concentration. PM 2.5 means that particulate matter smaller than 2.5 micrometer. And then you can assume this is the number of deaths due to a respiratory problem. So basically, this plot indicates that more aerosol in the air, actually they cause the more death due to the respiratory problem. So this is basically two words initial of the state: Kansas, Massachusetts, Tennessee, Wisconsin, Missouri, and Ohio, right? So let's assume we observe California aerosol loading is about 27 right here. Then we can also make a linear line among these data points. Then we can kind of predict what's going to be the mortality due to respiratory health issue when the particulate matter is about 27. gonna be about 0.1, whatever that unit is, right? So we call it that it as interpolate. Okay, this is two kind of way to you can predict or kind of predict the date that the kind of predict something based on this plot. I don't have a thing here, so this is how you can read usefully the plots. So we'll talk about finally pollution today. So we'll talk about some old issues of air pollution, all the way back to Roman Empire, even before. So you may surprise that the fact that even old days we thought we may think that it should be pretty clean, but some part of the world actually suffers the air pollution problems. And then you may realize by taking a look at the history of the air pollution that once that new technology is coming along, then there is always it is associated with the environmental problem once that technology is start to be used widespread in specific region. And then we'll talk about what's the consequences of the industrial revolution, the start of the steam engine use for the air pollution. And then we'll talk, mostly we will today talk about the air pollution from the coal. Obviously these days, still in the US, we use coal a lot in terms of power generation, but we don't have that much of the coal, at least air pollution issue from the coal these days, due to we have some processing technology for the coal. So we will discuss a little bit about clean coal technology, its pros and cons today. So if you take a look at the textbook chapter 4, page 73, it said, so available data suggests that air pollution in ancient Greece and even Roman Empire, there's some air pollution problem. How do we know about this? So one way we can find out the air pollution problem in the back in old days is start taking a look at the ice core. So we have a long history of the air. If you go out to the very cold place like Antarctica or Arctic region like Greenland ice pack, so basically this ice core has the history of air inside the kind of the small space inside of this ice core. So it is some of the scientists actually going out to the very cold place to sample this ice core, kind of a long ice core, to make a measurement what kind of air is trapped in the ice core. So it is a little difficult to imagine what's going on just by taking a look at the photo. So let's take a look at this video here.
2,500 years worth of ice from West Antarctica. This is part of a big national project aimed at uncovering climate history and glaciology in this region. Ice cores are a really great way to look at climate history. They're not the only way, and for certain locations on the Earth, you can't use ice cores. But at the poles in Greenland and on the Antarctic ice sheet, ice cores are a great high-resolution record that allow us to look at hemispheric and global scale climate change. There are plenty of other really good ways to look at climate history. For example, corals, tree rings, lake sediment cores, ocean sediment cores, and every different type of record allows you to address a question in a different way or in a different location. We are melting an Antarctic ice core for the Waste to Guide project. And here we have a melting system. We come in here every day, 10 hours a day, and melt as much ice as possible. And it's a way to look at the interaction with the atmosphere, the ocean, and the Earth's surface itself. We're measuring the water flowing by continuously. So we get a dust record and a conductivity record. And both of those things have an annual variation in them. And so in those wiggly lines, you can see an annual signal, kind of like tree rings. And we can't really see that in this ice, but as we look at the chemistry that comes out of the ice, we can see that annual record. I'm going to turn up the pump. So we have a clean lab where we melt the ice core. The ice is melted from one end to the other on a hot plate. You can hear the sound of the core. It's pretty neat as the as the ice melts. And the water is pulled through that plate, allowing us to get the inside of the ice core without ever having the outer part contaminate that inner part of the core. For the ice that we're melting today, a single year is about this much ice. And so if you imagine the stuff we're measuring on a really high resolution, through that year we can see changes happening and actually figure out what season these changes are happening. You can reconstruct the temperature of Earth, or the local regional temperature, so Antarctic temperature. You can reconstruct the strength of the winds, or the strength of the atmospheric circulation around Antarctica. We also see volcanic eruptions, and actually today we'll be melting ice that may show evidence of an ancient volcanic eruption, which would be very exciting. So these are top up arrows. So the top of the core is here, and we melt top to bottom. And that way we can connect all the segments of ice, because they're in 1 meter segments, and create a long record. Minus 20 C. Not that much colder than a typical winter day in Maine, but still cold enough to suit up. I am prepping the cores to melt. So I need to clean the ends of the cores. There might be some dust or particles that have just sort of stuck on the ends. So I scrape those off and get the ice into its core tray. These are ceramic blades, so they should not contaminate the chemistry of the core, and we clean them every day. Everything in the ice core world is very sensitive, because these are pristine records of ancient atmospheric chemistry, and we have to treat them that way.
I mean, I'm helping Bess track volcanic eruptions in an Antarctic ice core that spans back to 2,300 years. I mean, where else am I going to get experience like that?
2.5 centimeters a minute. We actually had a really interesting conversation out in West Antarctica. The fact that we're taking about 2 miles of ice and slowly drilling it over the course of 3 years, and then melting it all, and then analyzing it all. It's such a huge project that you can't really see it all at once. It's like you have to walk the distance of 2 miles to understand how much ice there is. It's just astonishing to think about what was happening in the world at that time, and the fact that this ice records the snow that fell at that time in Antarctica.
I guess that's it. So you can visually see what's going on in terms of the ice core business. So actually there's one research group in the systems science department actually doing this kind of analysis. The analysis is trapped in the ice core. So basically ice core has a history of the whatever thing in the atmosphere by accumulating the ice just year by year. So we can just do some analysis, chemical analysis of this ice core. Then we can reconstruct the previous air chemistry by measuring the ice core sample. So this is some of the example. So this is lead that we talked about last lecture. So this is the history that reconstructed by the some historical literature, how much of the lead has been used past about 5,000, 6,000 years, right? So this is based on our estimation based on the history. So again, you gotta read the x-axis, and then what's the y-axis? So x-axis is this is 0, means the present day, and then this the year before present, right? So it's 5,000 years before. So according to a history book, it seems like the use of lead has been increased quite a bit till Roman Empire. It is decreased a little bit, and then increased again recent days. So this is what we observed in the ice core. As you can see, the lead concentration in recent days kind of skyrocketing due to we use this thing too much. That means that there's a lot of lead actually in the air that is deposited on the ice in Antarctica or the Greenland, wherever you can think of. So this means that the lead is kind of has been widespread, and then the concentration of lead in the atmosphere has been increased quite a bit past 1,000 years due to people's use of the lead, right? So another example is copper. So this is kind of a different scale. So this is the day right now, year 0, which means right now. And then this is 5,000 years before, right? And then y-axis here is basically copper production. So same thing, the use of copper has been increased, and then after the Industrial Revolution, it's kind of skyrocketed based on the production of copper, which is reconstructed by historical record of the copper mining. And then this is actual copper concentration that are measured on the ice core. It's telling the same thing, that the copper concentration in the ice core has been steep increase past a few hundred years, right after the Industrial Revolution, right? So we will mostly talk about coal today. So first widespread use of coal was about 12,000. At the time, it was not mining. It was mostly from the coal that was found on the beach. So on the beach of the Scotland, there's people could easily find the coal on the beach. So you can read this description. Basically, it is kind of located in the ocean, and then it just kind of bringing to the shore by the wave, and then it kind of deposited on the beach. So people bring that things out, and then start to use this thing to heat it up. So literally, if you touch the charcoal, things like that, basically charcoal and the coal is about the basically same chemical composition. You have the pretty dirty hand if you just directly touch this thing. But we are not using coal that much these days, other than the this grill thing. So you may think that, oh, this is great thing. That you may think that grilling, things like that, you may, sounds delicious, but that was not the case. Firstly, we use this thing. So the first use of the charcoal, coal, that was found on the shore of the Scotland was using to make this chemical species, calcium CaOH2, which is basically can be used as the building material. So this is chemical processes. So if you are a little bit allergic about this chemical reaction, things like that, what you need to remember from this reaction is that it requires heat to get from calcium carbonate to something that can be useful to our life, right? So to generate the heat, you need some sort of fuel. At the time, the available fuel that can get to this high temperature, which is 800 degrees Celsius and then 1500 Fahrenheit, was the only coal. So there was no other alternative at the time. So they used the coal to heat this material you can find in the nature, calcium carbonate, to make another chemical species that you can use. Basically, this thing is the cement that you can just make a nice brick out of it. So you can just make a building, all sort of thing, use this thing. So it has been used widespread. And then let's think about why coal is generating air pollutants, and then what kind of air pollutants are coming from the coal. So this is one of the examples of the actual chemical composition of the coal. So this is a little overwhelming, but just bear with me. So what's the each stick it stands for? It's kind of we learn about this is a chemical bonding between carbon and carbon. I explained that we scientists are so lazy. This stick thing means that there's a carbon and carbon here. So there's all sort of a stick there. So basically, in each point of this stick, there's carbon there. So carbon, 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 carbon. You can make a nice ring or like this, and then very complicated structure. And then if it is not carbon, you're supposed to notate what that specific atom is. You can see the sulfur here, and then some of the hydrogen and oxygen. So in the bottom line, most of the coal are composed by carbon, and then hydrogen and oxygen and sulfur. All right? So maybe there are some sulfur here, carbon here, things like that. So if you heat it up, this thing. So if you heat it up and then make reaction of the some specific compounds like this, then there's oxygen, molecular oxygen in the atmosphere, somehow combined with this thing. So what you are gonna get in case of carbon, so let's so in terms of carbon, and there's oxygen. So what you are gonna get out of it? CO2. So this is complete combustion, but if it is not complete combustion, we call it incomplete combustion. It ended up CO. So CO2 and CO is coming out this direction. And then there's some minor portion of sulfur out here. What you are gonna get? Sulfur dioxide, right? SO2. So this and this are EPA designated air pollutants, right? So if there's too much concentration of this thing, it's harmful to humans. So, and then on top of that, what you can expect, the emission in terms of the coal burning, you can see it is quite dirty. So a lot of kind of dirty stuff, soot, can be coming out from this coal burning. You can actually see kind of black stuff is coming from this kind of charcoal grill burning. So probably it's much easier to understand what's going on in terms of particle emission is coal burning. So it's supposed to have this thing on the iClicker question, but iClicker is not still functioning in this classroom. So everybody is getting the credit today again. So the answer for this thing is the ozone. As I explained to last lecture, ozone is actually not emitted directly from some processes. It's actually formed in the atmosphere by chemical reaction. So we are going to discuss about it actually next class. So there was a first policy because the use of the coal was so widespread. So this king just made a new law that kind of prohibit using of the coal in the UK. But the problem at the time was that there was no substitute, the alternative way to generate that heat that needs to make that the stuff that you need to build the building or houses, things like that. So this law basically just doesn't work. So as you can see, this king has a sword on hand and a kind of authoritative kind of thing, but there's no alternative way to deal with the life. So simply kind of a regulation, couldn't work. Even at the time, the king actually has all sort of authoritative power and with a sword, things like that. But basically, it was the failed policy. So at the time, it was mainly used to generate that building material. But people start to use these things some other different ways. So for example, glass blowing, you need heat it up to melt the glass, in this case silicate, to make the glass stuff like cup or things like that for people's life. And then furnaces start to use the coal. And then even just making the beer, things like the brewery, you need some energy. You need to boiling up the, I don't know if that process is, but obviously they start to use this thing, all sort of things. So widespread. So the consequences is going to be the pollution in the regional, especially in the city. And then another important thing, so we took a look at what kind of things are coming out from coal burning. And then the other thing is that I told you that we love to kind of conceptualize atmosphere as a box. But this box size is keep changing. So in the winter time, usually temperature inversion is happening. What that means is that if you I just make a plot right here. So this is altitude, and then this is temperature. Temperature inversion means that in the surface, temperature is lower than the temperature up high. So temperature profile gets like this way. So as you are going up high, the temperature is getting increased. So what's the consequence of this thing? Is that you have very stable atmosphere. Basically, there's no mixing is going on in the atmosphere because that cannot be happening right here because you have lower temperature on the surface, which means that the air on the bottom is heavier than air on the top, right? So it's going to be staying right there on the surface. So basically, this structure of the air making this box very shallow. So if you are emitting air pollutants in here, then it's going to be mixed in the shallow layer on the bottom, right? So if you have a big box, if we assume in the summertime the temperature out here is higher than the up high, then actually the circulation is going to be happening, which means that, let's use different color. So this case, when circulation is happening, your box is much, much larger than this case, which is usually you can see during the winter time. Then if you have the same amount of air pollutants are coming into in this box, then it's going to be diluted into bigger box, then actual concentration is going to be much smaller, all right? Everybody's with me? So this is basically what the importance of the meteorological setup in terms of air pollution, all right? So real punchline that the use of coal has been widespread is the use of the steam engine. So steam engine, that sounds very complicated, but have you guys cooked any ramen noodle, things like that in your home? So what you're gonna do, the first thing you gotta do is the boiling the water, right, in the pot. Then usually you get hungry, then you gotta put the cover on top of it, right? Then as time going by, you know, it's just boiling the water, and then you just make a phone call in front of the computer, what's gonna happen? Then it's gonna be boiling off from your pot. Why that is happening? Because of there's some energy from the steam inside the pot. It's kind of removing the cover you put on top of the pot, right? So kind of this is the same thing. So if you take a look at this, at first it was used as the water pump. So you kind of make a duct from the water, river or whatever. And then there's you just boiling the water inside of it, and then generating the power from the steam, so that you can push this water to top of the this water level, right? So this is one application of the steam engine. So this is a little fancy way to use the steam engine, but the principle is the same as the previous one, and then one you use in your home when you cook the ramen noodle, right? So basically this thing is the boiling the water, and then push this piston, and then make the kind of up and down motion, so that at the other end you can use this end as the water pump, all right? So it's getting fancier and fancier, and then what? The English engineer developed this fancy engine that was used for locomotive, right? So this is a very cool way to you know, move around here and there. So you can still see this kind of locomotive here and there just for the fun, and then kind of people getting excited about this loud locomotive these days. But you can see there are two kind of the kind of visible steam thing coming out from this thing, right? On the bottom, you can see the white stuff. So what that's gonna be? It's gonna be probably steam, right? The water. And then what's gonna be this thing? It's from coal. So we don't want to have this stuff. But although you cannot see from this photo, but there should be a lot of CO2 and CO and SO2, right? So main air pollutants from the coal burning is CO2, CO, and SO2. So obviously this caused a lot of problem, but at the time there was no alternative other than coal to use the kind of mass transit. So people just need to just move around here and there. So they need some transport, mean, but there's no other way actually make that kind of efficient transport other than using steam engine. So there's a number of different law had been coming along in 1800, but it basically all failed because there was no alternative again. There's the UK, and then you can actually see the smog in the artwork. So this is Monet's kind of portrait of the UK in London. It's very, very hazy. Although there's sun right there, it's very hazy. You may think that this is artwork, but this is kind of portray of the how dirty it was in terms of the air in late 1800 in London. Obviously these days, usually visibility is pretty good out there, right? So US also at the same time, it was a lot of problem. So a lot of cities actually made some ban in terms of the some regulation in terms of air pollution, mostly from steam engine. So some of the cities listed here, Pittsburgh, Cincinnati, Chicago, and St. Louis, they are all Midwestern part of the country. That was actually the main part, actually a lot of industrial manufacturing was going on in that time, frame. You can basically read through. So people start to call it as smog. It's early 1900. The smog was firstly introduced by the in UK, and then basically a combination of smoke and fog and the smog. So it is not really a scientific term, but people just start to call it. But it makes sense that in London there's a lot of fog out there, but this kind of mixture of the smoke from the steam engine actually made a lot of problem at the time. So London type smog is that mostly coming from, first, the material, the source of the air pollution that London type smog is coal. And then specifically coal burning make the CO, CO2, and SO2, and then the aerosol, particulate matter, to the atmosphere. And then the other factor of the London type smog is the temperature inversion that makes the mixing depth of the atmosphere much lower. So usually the London type smog is happening during the winter time, right? So there's two important factors: the coal burning and then temperature inversion in the winter time. So we'll take a look at a couple of old photos that basically you can see. If you take a look at the tree, although it's black and white, you can see a little bit of snow there. So basically this is winter time, right? And then you can see a lot of chimneys is emitting the black stuff, which is from the coal burning. So again, this is combination of the meteorological environment, which is during the winter time, and then people's emission of the air pollutants, mostly from coal, which emits CO, CO2, SO2, and then particulate matter, right? This is Youngstown, Ohio. Again, this is hub of the US manufacturing hub at the time in early 1900. You can see a lot of chimneys emitting black stuff. And then there's no snow, things like that out there, but it's probably during the winter time. So if you take a look at the older, there's no trees actually even around there. It's hard to guess that it's actually whether it's winter time or summertime. It's usually those kind of London type smog is happening during the winter time. This is Gary, Indiana again. I think it's also a winter time and a lot of emission from the chimney, the black stuff coming from coal burning. So on top of those kind of coal burning, last lecture we talked about the lead added fuel. So on top of this stuff, that CO2 and SO2, and then particulate matter, mostly composed by carbon, and then lead is also emitted to the atmosphere because of the leaded fuel, which is started used in the early 1900s. So we discussed about this thing by watching the video last lecture. So I'm going to skip this thing. So all sort of problem was coming from that lead-added gasoline, but basically this engineer who developed this thing denied all the side effects of the lead, so that caused a lot of problem, and that has been used even till 70. Although we found the potential problem of the lead-added gases in 1925. So after 50 years of this initial incident, basically we did nothing because of the controversy between who advocate using the lead-added gasoline and then who oppose this lead-added gasoline kind of thing. So we discussed about this thing, and then this is Pennsylvania in 1948, the same thing. And then this is kind of striking photo. So this all light is lit up. You may think this is night, but this is actually noontime in Pennsylvania. So this is October again. So it's October late October in Irvine. It feels like summer, but out there in the Pennsylvania, probably it's pretty cold. And then probably the temperature inversion happened, and then a lot of emission going on. There's cars, and then the coal emission to heat it up in the inside, and then that kind of get trapped because of this temperature inversion low boundary layer depth. So people usually doing nothing until really, really big incident happened. So one really, really big casualty caused by this smog has happened in 1952. So this is same thing, 1952, it caused about 400 deaths. You may think this is really, really old problem, 1952, maybe your parents, even some of your parents may be younger than this. But this same thing is actually going on some part of the world. So let's take a look at one example. So this is news clip early this year in the US. I think that's it.
Now we're going to show you video of something happening right now that has hundreds of millions of people buying masks and hiding inside. The Chinese are in the throes of what reporters are calling airpocalypse. And ABC's Gloria Rivera is truly there in the thick of it all.
The sun was shining in Beijing today, but you wouldn't know it. Just being outside can make eyes itch and throats burn.
I feel like a little bit suffocated.
This could be my lung, tweeted one Chinese resident, and time-lapse photos showed how chemical clouds made buildings disappear. Zero wind, freezing temperatures, and factories going full tilt made this week a perfect storm for pollution. At its peak, pollution hit 755 in Beijing, making breathing extremely hazardous. By comparison, the worst polluted city in the U.S., Bakersfield, California, hit a high of 159 last year. It's super toxic air.
Particle pollution like that can actually cause heart attacks and strokes that can kill people. It's lethal.
This photo from a recent Greenpeace study shows what an air filter looks like after just 24 hours in Beijing.
Watch me wipe a thin layer that's accumulated on most cars. That's soot and grime. And this is my own air purifier. Watch this. Look, that's what we're breathing in Beijing. One expert told me it's like becoming an instant smoker.
Beijing did issue emergency warnings for the first time ever this year, signs the government can't avoid problems everyone can see. Gloria Rivera, ABC News, Beijing.
And another note about this, when our team visited China 2 years ago, we noticed the difference between the polluted air outside of Beijing and how we felt when we walked inside the American embassy, where the air was much cleaner. Well, we were told that the pollution is so severe there because of health issues, the embassy creates special filtered air for embassy workers, so they'll have air as clean as the air here back home.
So this happened early this year. So basically, I don't know you catch that thing or not. So it talked about all those industrial facilities are full swing. That means there's a lot of emissions are going on. and then it's freezing cold zero air, means that you have smaller box. Basically, the air is stagnant on the surface of the atmosphere that actually accumulates the air pollution much more efficiently if there's a small amount, if there's the same amount of air pollution emission out there in the city. So basically, the problem is we basically in the whole world send all the manufacturing facility to China, and then that's actually what actually causing the problem, right? So we used to have in the U.S. when Midwestern part of the country was the hub of the oldest industrial facility, that we had the same problem in the U.S. And then we basically sending this manufacturing facility to China, not only U.S. Also Europe, and then now it's just Asians turn that suffer this kind of London type smog. So I read an article a couple of years ago in National Geographic. Basically, one small town in China, actually they are producing about 90% of socks the people are wearing all around the world. So that's kind of that what we are doing is sending all those manufacturing facilities to Asian countries. So anyway, so this is the one of the big accidents that happens in 1952. It was kind of perfect storm that everything kind of happened at the same time. In the winter time, a lot of the emission of the air pollutants. So you can see this is again the daytime, but still you cannot see that well the outside, and then people need to lit up the light in the street even during the daytime, right? So although it's a smaller scale, the same thing was happening many different years, even early 60, right? So there's a kind of describe about the synopsis of this incident. So because I talked about it happened usually winter time, it's pretty cold outside, so people burning the coal to keep warm inside, right? So this emission is going on. So kind of the feedback is going on. Air is getting colder, and then so you are having the smaller boxes. The air gets stagnant on the surface more, and then because it's cold, people are burning more coal inside the house, and then that's emitting more the air pollutants in there, and then the concentration of the air pollutants in the air people breathe is getting higher, right? And then at that time, immediately after World War, and the people were using their low-grade, very high sulfur coal. People used at the time in London that may produce high sulfur coal, produce the more SO2, which is toxic, right? Produce more SO2. And then at the time, early 50, they start to use diesel-fueled buses instead of the electricity running the tram thing. So this also added more pollution in the air at the time. So there are three different things in terms of the air pollutant emission issue. And then it's December, obviously. And then the high-pressure system. So again, if you read through it, basically that's what I explained right here. Your layer that can mix the air pollutants on the bottom of the atmosphere is much shallower than other time because of the cold temperature and then high-pressure system. So this thing was going on until there was rainstorm. I think there's a couple of weeks or something like that. So during that time frame, obviously, first thing you can see is the visibility. So if you read this thing, basically people cannot see even a few feet ahead of you, and then if even some people describe that you cannot see your feet on the street because the visibility is so horrible, right? It's out there, the street of London. And then this is another description of how bad it is in terms of visibility. So why visibility is such a horrible? Because there's so much particulate matter in the air, and then obviously there's no other way you gotta just breathe it. So that is gonna be just accumulated in your lung, and then it start to cause health problems, right? So this health impacts 4,000 people die directly due to this the air pollution issue, basically the respiratory health issue, mostly young or elderly. And then in terms of the other injury and then other health-related issue, the number of people who suffer that kind of problem was somewhere around the 6,000 to 25,000. It was kind of a mass-scale thing at that time. So this is so humongous. So we call this particular type of the air pollution problem called as London-type smog. And then in the developed world, there's not much of this thing going on in terms of London-type smog because we are not using coal as much as in those days. But still, although developing world like China and then East Asian country use not much of that kind of dirty coal that much these days, but every facility is so concentrated, still you can find this kind of London-type smog that associated with the wintertime shallow boundary layer depth meteorological setup. You can still observe those kind of London-type smog in the developed world, okay? Developing world, actually. So we will shift gear to California, Los Angeles, California. So this is supposed to be an iClicker question, but iClicker is not working. So, so this is, I think, Youngstown, Ohio in 1909, early 1900. And then this is Los Angeles on top of this thing. Can you tell some differences, any obvious differences between Youngstown, Ohio, and then Los Angeles in early 1900? What's that?
There's more buildings.
There's more buildings. That's a good point. Then what's not here, and then what's here? Factories. There's no chimneys. You cannot see any chimneys around here that emitting this black stuff, right? So that that means the emission of air pollutants from human activities should be very different from this manufacturing facility and then this mostly heavily resident area, right? So let's shift the gear a little bit to this side. So at that time, the fuel people mostly used was the, because it's people running the car, was the gas, right? Gasoline. So by just take a look at this, the gasoline looks much cleaner, right? In terms of just if you just touch this thing, it may be more smelly, but you know your hands is not going to be as dirty as this coal, right? So so we will talk about this emission from the this gasoline a little later. But let's talk about clean coal technology. This is going to be last topic we discussed about the coal. So still, coal is most dominant way to generate the electricity in the U.S. So this is from 2004 to 2013, and then this is fraction of the origin of electricity. So about 50% of electricity in the U.S. is generated by coal-powered power plant. And then the use of the prediction of the use of coal is going to be increased quite a bit. So in the U.S., probably we are going to use about the same amount of the coal. And then rest of the world, this is the prediction. It's going to be about the same from 1990 to 2030. But the kind of the rising economic power, China and India, is going to use a lot more coal than the it used to be, because its kind of energy needs should be satisfied to generate the electricity, right? But these days, people just developed a lot of different ways to process this coal burning much cleaner way. So if you take a look at this website, so this is industry website that advocate actually coal technology, coal use, things like that. So if you look at this,
coal technology refers to technologies that improve the environmental performance technologies include devices that increase the operational efficiency of a power plant, as well as those technologies that reduce emissions. Coal. Coal is mostly carbon. When coal burns, it creates the greenhouse gas carbon dioxide. Coal also contains sulfur. When coal burns, the sulfur is converted into sulfur dioxide. When coal burns, nitrogen in the air and the coal are converted into oxides of nitrogen. Unburned coal contains impurities that are collectively referred to as particulate matter. Coal contains trace amounts of mercury that are released when it burns. Advanced control technology for oxides of nitrogen. Oxides of nitrogen are combined with ammonia and a catalyst to form harmless nitrogen gas and water vapor. Advanced mercury control technology. Mercury can take different chemical forms depending upon the coal source. One means of reducing mercury involves injection of activated carbon into the flue gas stream. The mercury sticks to the carbon that is removed by an electrostatic precipitator or fabric filter. Some species of mercury can also be removed by the sulfur dioxide scrubbing process. Typical particulate removal. Particulates are removed from flue gas either using an electrostatic precipitator or fabric filters, sometimes referred to as a baghouse. Removing particulates using an electrostatic precipitator involves electrically charging the particles so the electrostatic precipitator can remove them. Fabric filters are like gigantic vacuum cleaner bags hung in a baghouse through which the flue gas passes. Particulates are trapped in the bags and removed. Typical sulfur dioxide scrubbing. Sulfur dioxide in the flue gas reacts with limestone or sometimes other chemicals to create a solid material. The solid material is collected for disposal or reuse. For example, sometimes the waste is converted into gypsum, which can be used to manufacture drywall. Carbon dioxide reduction. Power plant emissions are regulated by the Federal Environmental Protection Agency and by state and local authorities. Capture of carbon dioxide becomes an additional step in the pollution control process. With most of the pollutants removed, the flue gas is emitted from the power plant stack.
That sounds great, right? So we gotta use the coal more because it's burning so clean, and then we have all the technology. But again, this is the kind of website from actually industry sponsored the website. So there's some other story behind of this clean coal technology. So let's just watch this thing.
How the skyrocketing price of oil was making it necessary to drill in environmentally sensitive areas of our own country. The U.S. has some of the world's greatest reserves of coal, which could replace oil. But coal has always been considered a so-called dirty fuel, bad for the environment. But now utilities are testing technology to try to make coal clean. Wyatt Andrews has the facts in tonight's Eye on Energy.
And this clip is from the 2008. So
coal is by far the dirtiest way America makes electric power, but you wouldn't know that from this ad campaign funded by industry.
It's the resource that generates half of our electricity.
A campaign promising a future of clean coal.
Clean coal, America's power.
And it's not just industry. The presidential candidates are also pushing
2008.
coal.
A way to produce coal-generated power cleanly.
We can have clean coal technology.
But what is that technology?
Is this what they call clean coal? This is the cleanest coal-fired plant in North America.
The cleanest coal plant in North America is operated by Tampa Electric in the middle of rural Florida. What makes it clean is that they don't burn coal exactly. They mix it with water and oxygen and convert it into a gas.
Much lower sulfur dioxide emissions.
According to company president John Rammel, gasifying coal allows the company to remove pollutants like sulfur, nitrogen, and soot, which virtually eliminates acid rain.
You can do it much cleaner than with the conventional coal technology.
That's the good news. Here's the problem.
There is no such thing as clean coal today.
James Hansen, NASA's expert on global warming, says all coal plants, even Tampa Electric's, still emit millions of tons of carbon dioxide, the most threatening greenhouse gas.
There's no coal plant that captures the carbon dioxide, and that's the major long-term pollutant.
But if carbon dioxide pollution is the problem with clean coal,
Scientists say there's a solution. They believe it's now possible to recover most of the CO2 and store it underground. The idea is called capture and sequester, and today a global race is on to learn how it should be done. One Norwegian firm is storing tons of CO2 in rock caves beneath the North Sea. America's efforts to sequester carbon have stalled. The Department of Energy planned to fund a plant seen in this animation, but pulled its funding when the price grew too high.
It took 7 years just to decide where they were going to make a pilot plant, and then they decided to cancel it.
And now the failure to solve the CO2 problem is a threat to coal itself. In the last 5 years, at least 63 coal-fired power plants have been scrapped or defeated by public opposition.
No more coal. No more coal.
Florida's Governor, Charlie Crist, even helped pull the plug on 2 clean coal plants because he says without a carbon solution, forget clean coal.
Until that time comes, we want to develop more solar, more nuclear, more wind.
Which is why the industry needs an ad campaign.
A commitment to clean.
Until the federal government funds the research on carbon dioxide, America's reliance on coal is in long-term trouble. Wyatt Andrews, CBS News, Polk County, Florida.
So basically, we talked about coal burning emits a lot of particulate matter, SO2 and CO that cause a lot of problem in early days, maybe 100 years ago and 50 years ago, immediately after Industrial Revolution. But now we have technology to remove some of the air pollutants that we are interested in. But the problem is there's no good way to remove CO2. So there's some controversy about this clean coal technology. So I will ask you your opinion on this clean coal technology. So you can watch this thing, the homework set that I will give this Thursday. So you can take a look at this YouTube and then the website. This is advocate for the clean coal technology. And then this website, they strongly oppose their clean coal technology. I think this news clips right here from CBS kind of balanced approach that this side and that side, opinion, things like that. So I want to hear your opinion on this technology, all right? So now let's shift the gear, the air pollutants from the car. So we call it internal combustion engine. So your car basically has this thing. Every single car has this thing, except that you have electric car. Even electric car has that thing. Your plug-in hybrid has that thing. I think only thing doesn't have this thing is the go-kart kind of thing. Even go-kart should have it, or the club car in the golf area, things like that. And then what's that thing? What's that thing that electric car maker? Tesla. Tesla car doesn't have this thing. It's just all battery operated. So basically, this is the same thing, same idea of that steam engine. So basically, use this gasoline. This is chemical composition of the gasoline. Then make the motion of up and down, and then make the rotation motion so that you can just move the wheel going, the rotation motion. So again, let's take a look at this fuel. So don't freak out, this chemical composition. So let's take a look at what's in there. So it's all carbon, 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 and oxygen. There's no sulfur in here. So this kind of car, the fuel, the gasoline, wouldn't emit SO2. So it's going to be mostly CO and CO2, right? And CO2. And then if you go back, see this thing, and then gasoline, it's much clean, right? So it doesn't emit that much of the particulate matter when it gets burning. But the problem is, the interesting aspect of this internal combustion engine is that temperature is so high, 1900 degrees Celsius, and 3600 Fahrenheit. So I told you that nitrogen and oxygen are very inert, which means that it's not really participating on the atmospheric reaction. But because the temperature is so high, so basically there's triple bonding for the nitrogen atom that makes up molecular nitrogen. In terms of oxygen, there's double bonding. And because there are a lot of bondings in there, it's kind of the bonding strength is very strong. So you can understand that way. So if you just have the excess heat in this bonding, you can actually break up this bonding. Although it's a very stable molecule, in normal condition, it wouldn't, the bonding would not be broken, but the temperature is so high, so this gets broken up and then making NO, nitrogen oxide. So this starts to cause all sort of problems. So we'll learn about this thing, what this thing is causing all sort of problem, especially in Los Angeles and area and then modern world. So this is the source of the problem. So there are a couple of old historic photos again. So there's not much of industrial facility, but a lot of buildings and a lot of cars, right? This is the airport at the time, back in 20s. So this is Los Angeles in 1930, although you can see the one chimney there, but not much of a thing, but you can see there are a lot of houses, but a lot of cars. It's a home of the freeways out here, right? Just people just driving everywhere. People that do not use the public transportation even these days. So just like the previous photos you saw in all those area that heavily use the coal as the energy source, you can see the smog thing all around the Los Angeles, where this thing is coming from. So let's talk about it. So one thing is that open waste incineration, because there's too many people, it's populated, and when people has the waste in their house, they just burn that thing on the backyard. So that's one pollution source at the time in Los Angeles in mid-1940. And then obviously it's car. And then I don't know, can you see this thing or not? This guy is driving a shiny car, but wearing the gas mask literally, right? So that was this bad that people are actually wearing this kind of a gas mask at the time, 1950. So this is one aerial photo. So basically you cannot see anything in the Los Angeles basin area. So even people walking around the street, and then either there's two ways you can deal with it. So you have a handkerchief or the gas mask at the time. It's so severe at the time. So it's still a problem, but in 1960 and 70, it was a big problem. You can see the layer of the air pollutants right here. So this is New York City. So big city also suffered this kind of problem, but not as much as the Los Angeles. So there's a lot of problems that cause the health problem of the respiratory health due to this the air pollution problem in Los Angeles. This is LA residents, non-smokers' lung, but you can see there are a lot of particulate matter kind of deposited into the lung. And then not only that, there's a lot of plants actually get damaged by this air pollution at the time. So next class, we will talk about mostly finding that scientific finding. Oh, it's not over yet. It's not over yet. From the mid-1950, actually that scientific study was initiated by this scientist, again, Ari Hagen-Smith. He was a professor at Caltech, and then he actually developed a lot of idea what caused this Los Angeles type smog in the lab at Caltech. So basically, what he was doing is that he just basically putting the air pollutants in this glass jar, and then he's actually making the reaction that is going on in the atmosphere in Los Angeles at the time by putting some air pollutants in here. The problem at that time mostly caused all those air pollution problem in Los Angeles was ozone. I talked about it 3 or 4 times, I think, during the course of this course, past few lectures. So ozone is good thing if that thing is on top of the atmosphere, in the stratosphere, somewhere in between 20 to 50 kilometers. But it's bad thing if you breathe this thing, right? And then ozone is not directly emitted by human activity. This lather is formed by chemical reactions between the NO and NO2 from here, from the car engine burning, and then hydrocarbon, which is organic gases in the atmosphere. So there's two things you need to remember. Ozone is not directly emitted from the human activity. It's lather formed by the chemical reaction in the atmosphere. So what's the source for the atmospheric reaction? They are NO and NO2, and then hydrocarbon. So you should remember these two things about Los Angeles smog. So I think this is basically, and then to get rid of the problem of the waste burning problem, basically the backyard incinerator was banned in 1957. So all these seller who's selling this kind of fancy incinerator kind of disappointed about their decision. So that's one thing, just one emission source at the time was removed. So this kind of backyard incineration was banned. So if you take a look at this, in 1960 it was banned. So she got cited by burning her waste in the backyard. So in the 1960, this emission source got rid of from the Los Angeles area. So only problem still we have is that the emission from the car engine that emits NO and NO2 from this reaction. And then if you go back to this fuel, then collectively we call it the carbon structured compound. How we call it? Organic. So organic. So this is organic compound. And then basically after you refuel your car, it is smelly for a while, right? So what is the smell is coming from? It's from the gas, right? Why we smell it? Because this liquid stuff is very easy to evaporate into the atmosphere, and then we smell. The sense of smell is coming from the gas. So this compound, the organic compound, easy to evaporate into the air. Actually, that gets into our nose. Then we start to smell it, right? So smell is coming from the gas, and then taste actually coming from the liquid. So this is very easy to evaporate. So this thing is actually getting into the atmosphere, and then that actually makes the reaction between NO, NO2, and then this organic gases, which is reactive organic gases, and then that makes the ozone in the atmosphere. So that's where is the Hagen-Smith. So that's the reaction scheme. So next class, we will talk about this reaction. So I should warn you that next classes is going to be most difficult classes for this whole course. So getting a cup of coffee before you come to this class, and stay widely wake up. But after that, it's going to be very easy, so don't drop out.